Hey everybody, welcome back to chemistry, and now I need to teach you how to balance redox reactions. So redox reactions are a little bit more difficult to balance than your normal chemical reaction, and the reason is this. With a normal chemical reaction, all you need to do to balance it is just to make sure that for each element you're looking at in that chemical reaction, you have the same number of atoms of that element on the reactant side as you do on the product side. Now you also have to do that for a redox reaction, but here's the thing. Not only do you have to check for atom balance, you also have to check for electron balance. Now what does that mean? What that means is if you have a redox reaction, you have to make sure that the oxidation part of the reaction is giving up the same number of electrons that are being picked up by the reduction part of the reaction. And so you really have to do both of these things. If you do not, then your redox reaction is not balanced. Okay, so let me just kind of give you an example of a chemical reaction that is a redox reaction, and then I'm hoping that you can see that as written, it is not a balanced equation. So here we have a redox reaction, and you can see that it's a redox reaction is because you probably know at this point that the oxidation numbers of those monatomic ions will be the same as those charges, and you can see that those oxidation numbers for iron and tin are changing as you're going from reactants to products. Now, let's first check for atom balance. And so if you look at that equation, if you just look at the iron ions, you will see that there is one iron ion on the left, but there's also just one iron ion on the right. So iron atoms are balanced. Tin, there's one tin ion on the left, and there's only one tin ion on the right. So tin ions are balanced. Okay, now we have to check for electron balance. And so let's look carefully at the half reactions here. So one half reaction is we're following the oxidation of iron. And so we're going from iron 2 plus ion to iron 3 plus ion. In order for that to happen, then the iron 2 plus ion is losing an electron, so we write plus 1 electron there. Now, if you look at the other reaction, the tin reaction, that is a reduction reaction. And we can sort of see that is because the positive charge as you go from reactants to products is getting less. And so here we're going from tin 4 plus to tin 2 plus. Well, it's going from tin 4 plus, meaning it's tin that is deficient in 4 electrons, to tin 2 plus, which is only deficient in 2 electrons. And so it only needs to pick up 2 electrons there. So you can see that the top oxidation reaction is losing 1 electron, but the bottom reduction reaction is not gaining 1 electron, it's gaining 2 electrons. And so we have a problem here in that the number of electrons being lost by the oxidation reaction needs to match the number of electrons being picked up by the reduction reaction. So the only way you can really fix this problem is you need to learn how to balance redox equation using a bunch of rules, which I'm going to go over right now to the computer and explain to you. So here are the rules for balancing redox equations. So the first step is to write out the half reactions for the oxidation reaction and the reduction reaction. And the second step is for each half reaction, make sure that the atoms for each element are balanced. If they are not, then go ahead and balance them by adding coefficients where needed. The third step is to indicate for each half reaction the loss or gain of electrons in the reaction with an E- symbol. The fourth step is, if needed, multiply half reactions with a coefficient to make sure that the electron numbers are the same between the oxidation and reduction reactions. And the final step is you add up the reactants and you also add up the products to get a final reaction that represents your balanced redox equation. So I want to take this example reaction we were sort of looking at before, and I want to go through these steps to balance it. Okay, so the first step is write out the half reactions for the oxidation reaction and the reduction reaction. And so what I'm hoping that you can see is that as you follow iron from 2 plus to 3 plus, its oxidation number is going from +2 to +3. Therefore, it's getting more positive, and so this should be the oxidation reaction. Now let's look at the tin reaction. You can look at the oxidation numbers for tin. So for tin, the oxidation number is going to be +4 on the reactant side and +2 on the product side. And so you can see that the oxidation number is getting more negative, and so this should be a reduction reaction. So we've completed the first step, and so everything seems fine so far. So let's go to step 2. For each half reaction, make sure that the atoms for each element are balanced. If they are not, then go ahead and balance them by adding coefficients where needed. So what we need to do is we need to check for each half reaction, do we have the same number of that atom on the reactant side as we have on the product side. So what you can see here is that essentially in this half reaction, there's no coefficient here, so we have one iron ion. There's no coefficient on the product side, so we have one iron ion. So the iron ions are balanced. Now how about tin? Same deal, coefficient of one tin ion or atom if you want to call it that. And then on the product side, one tin ion or atom. So it looks like step 2 is complete in that it looks like the atoms of each element on either side of the equation are the same number. Okay, so we move on to the next step. Indicate for each half reaction the loss or gain of electrons in the reaction with an E-. Okay, so let's look at the first half reaction, which is iron 2 plus going to iron 3 plus. Let's figure out what it's doing. Is it losing or gaining an electron? Well, I'm hoping you'll notice that this is the oxidation reaction. And so you might remember Leo goes Gur. Leo is loss of electrons, is oxidation. So here you can see iron 2 plus is losing an electron, is becoming more deficient in negative charge, and goes to iron 3 plus. It looks like as we go from 2 plus to 3 plus, again, looks like we've lost an electron here. So I'm going to indicate that with a plus E- sign there. Okay, now let's look at the other reaction. So you can see here we're going from tin 4 plus to tin 2 plus, and so this indicates a decrease in the oxidation number. So this is a reduction reaction. So where do we put the E- side? Do we have it on the reactant side, which would be here, or on the product side, that is here? Well, we remember Gur, gain of electrons, reduction. So we need the electrons to be here on the reactant side. So the question is, how many electrons do we need to add here in this reaction to go from tin 4 plus to tin 2 plus? Well, tin 4 plus is deficient in 4 electrons. Tin 2 plus is only deficient in 2 electrons, so we only need to gain 2 electrons, and so that is correct. Okay, so we go on to the next step. Multiply whole reactions with coefficients to make sure that the electron numbers balance. So you can sort of see we have a problem here in that the oxidation reaction, for every iron 2 plus ion that is oxidized, 1 electron is released. Yet for the reduction reaction, for every tin ion that is reduced, you need 2 electrons. So how do we solve that problem? Well, what we do is you're going to basically take this whole iron reaction and multiply all terms, the ions and the electrons, by 2 in this way. So let me go ahead and do that here. So I'm going to multiply everything by 2, and so now we've done that, so that looks fine. Okay, and now what you can see is that we have succeeded in getting electron balance. We have 2 electrons here that are being released by the oxidation reaction, which are being picked up by the reduction reaction. So that went fine. Okay, so the next step is once you have balanced the electrons like that, add up the reactants and the products to make a final balanced equation. And so that's pretty easy to do. So note where the arrows here, and so I'm going to draw a line through the arrows here. So here are the reactants, we're going to add those up, and then here are the products, and we're going to add those up. And so I've done that here, okay? And when you do that, this is the reaction you get. This is the final reaction. Let me just erase all this stuff here. Okay, so look at the final reaction here. You can see on the reactant side, we have 2 iron 2+, and then SN4+, and so that's what we got from here by adding the 2 iron 2+ and the SN4+. And then on the product side, we have 2 iron 3+, and then SN2+, and we got those by adding 2 iron 3+ here and SN2+. Now you might say, what about the electrons? Do we have to add those into the final equation? The answer is no, because they cancel. We have 2 electrons on the product side, we have 2 electrons on the reactant side, and so they cancel out, and so that is the balanced redox equation. Okay, so now what I want to do is I want to go to the glass board and do several of these reactions. So let's go ahead and do the first one, okay? So the first one, let me just write this out, and I'm just going to write it out without state symbols. That makes my life a little bit easier. So we have potassium plus chromium ion gives us chromium plus potassium ion. Okay, so the first thing you may want to do is identify whether this is a redox reaction. And I think you might be able to see immediately that it is, and that the oxidation number for potassium would be 0, and the oxidation number for potassium ion is +1. So potassium's oxidation number is changing. Same thing with chromium, its oxidation number is changing. Therefore, this is a redox reaction, which means that you have to use the steps I just told you about to balance this correctly. When you use those steps in that order that I suggested, what you'll be doing is balancing not only the atoms, but also the electrons. So let's go ahead and carry out these steps. Okay, so you might remember the first step is to identify the half reactions as either oxidation or reduction. So we'll do that. So we have potassium here, so we have potassium. On the reactant side, looks like it's the neutral atom going to here, the product side. And so that is the potassium ion. So that's one half reaction. And then the other reaction is we have a chromium ion here going to chromium metal. So it may be useful to figure out the oxidation numbers of these elements and ions here. So potassium is a free element. Its oxidation number is 0 on the reactant side. It's going to be +1 on the product side. And so this, to me, looks like an oxidation reaction. Okay. Here, chromium ion on the reactant side has an oxidation number of +3. Chromium on the product side has an oxidation number of 0. You can see the oxidation number is decreasing as you go from reactants to products. And so this is a reduction. Okay. So the next step is to make sure that in these half reactions that the number of atoms are balanced here on the reactants and products side. And you can see with potassium we have 1 atom on each side, so those are balanced. With chromium we have 1 atom on each side, so those are balanced. Okay, so those are balanced, and so now we have to deal with electrons. All right, so what we have to do now is figure out how many electrons are lost by the oxidation reaction and how many electrons are gained by the reduction reaction. So this is what you do. Here's the oxidation reaction. It's going to lose electrons. How many electrons does it lose? Well, what I suggest you do is just kind of forget about the oxidation numbers at this point. And let's just look at what the atoms are doing in terms of electrons. We got a neutral atom here. It becomes positively charged by losing a negatively charged electron. It's gaining 1 positive, and so here what we're going to do is indicate that it's losing 1 electron like that. Now, how about the chromium ion? Well, we go from a chromium ion, which is deficient in 3 electrons, to a chromium atom as a product, which has all its electrons, so it needs to pick up 3 electrons. So what I'm going to do is on this side of reduction, put the electrons on the left side, so I put 3 electrons like that. Okay? So what's the next step? What we have to do is multiply half reactions by coefficients if needed, such that the number of electrons lost by the oxidation reaction is the same as the number of electrons gained by the reduction reaction. So I think what you can see is that you end up having to multiply the oxidation half reaction by 3. So let's see why we might go ahead and do that. I'm going to rewrite these reactions, and so we have 3 potassium metal goes to 3 potassium ions plus 3 electrons. Chromium reaction, we didn't really do too much to that, so it's 3 electrons over here plus 1 chromium ion gives you a chromium neutral atom. Okay, so finally what we can do is just check to see if there are as many electrons leaving the oxidation reaction as are being picked up by the reduction reaction. And there are, so these cancels out. So we have balanced the number of atoms here, and we've balanced the electron passing. And so now we can write the final redox reaction, which will be adding the reactants together. So it's going to be 3 potassium plus chromium ion gives you 3 potassium ions plus a chromium atom. So that is the balanced redox equation here. So one thing that's kind of remarkable is that you can now see that you need 3 of these potassium oxidations to give enough electrons for 1 chromium reduction. So that often happens in these redox equations. Okay, so let's move on to the next one. So reaction 2 is as follows. We have iron 3 plus reacting with magnesium metal gives you magnesium with a 2 plus ion plus iron metal. Well, first off, we might want to figure out this is a redox reaction. So I think you can pretty quickly see that this is a redox reaction because the oxidation number for iron 3 plus would be plus 3. For neutral iron here, it'd be 0. So the oxidation number of iron is changing, and also the oxidation number of magnesium is changing. So this is a redox reaction. So that means you have to balance both the atom numbers and the electrons being passed from the oxidation to the reaction. Okay, so let's go ahead and write out half reactions. So we have iron 3 plus is going to iron metal. And then we have magnesium metal is going to magnesium 2 plus. Okay, so let's go ahead and identify which of these half reactions is oxidation, which one's reduction. And so here in the iron half reaction, we have iron with a 3 plus ion, so its oxidation number is plus 3. Here the iron atom has an oxidation number of 0. So you can see the oxidation number is getting more negative, so this is apparently the reduction reaction. Okay, and then here magnesium goes from an oxidation number of 0 to plus 2. So this looks like this is the oxidation reaction. Okay, so the next step is we're going to balance atoms in each of these half reactions. You see that in the iron half reaction we have 1 iron atom on each side. The magnesium, same deal, so the atoms are balanced. Okay, so the next step is to put in electrons using that symbol into each of these equations. So let's focus in on the oxidation reaction first. So again, in the oxidation reaction, you have something that's going to lose electrons. So we have a neutral magnesium atom that is becoming deficient in 2 electrons. So it needs to lose 2 electrons like that. Now, with the reduction reaction, it's going to gain electrons. And so it's going to go from a 3 plus state, means that iron is deficient in 3 electrons here, to a neutral state, meaning it has all its electrons. So we have to add 3 electrons here. So that's fine. Now we have to make sure that what we can do is that the oxidation reaction will pass as many electrons as the reduction reaction will get. So we have to deal with that. So you see the oxidation reaction as it's written passes 2 electrons. The reduction reaction gains 3 electrons. So how do we remedy this? Well, let's go ahead and multiply the entire equation with a coefficient of 3. And then you can sort of see here that the oxidation reaction will pass 6 electrons. For the reduction reaction, we're going to multiply it by a coefficient of 2. And so the reduction reaction will pick up the same number of electrons, which are 6. So let's go ahead and rewrite those. And so we have is 6 electrons plus 2 iron, 3 plus, gives you 2 iron. And then here we have 3 magnesium, gives you 3 magnesium ion, plus 6 electrons, okay? And so now you can see that the 6 electrons here on the left side cancels out with the 6 electrons here on the right side. And then what we can do is add up the reactants and the products. And so let me do that. So I have 2 iron, 3 plus 3 magnesium gives you 2 iron plus 3 magnesium 2 plus. And since you have balanced the atoms for each element and you balance the number of electrons passed between the oxidation and reduction reaction, this reaction here should be a balanced redox equation, okay? So what I'm going to do is I'm going to let you do the third one on your own, and I may ask you a question about that. Okay, let me go to the fourth and final reaction. This is a little bit trickier, okay? So we have lithium. I'm going to leave out the state symbol, but it's in the metal form. And it's going to be reacting with chlorine. Again, leaving out the state symbol, but this is in gaseous form. And it's going to produce lithium chloride. And notice there, lithium chloride is in a solid form. Remind yourself that lithium is a metal. Chloride here is a nonmetal, and so lithium chloride is an ionic compound. So when you here see this ionic compound, imagine that this is made of lithium ions and chloride ions, and so that may be helpful to remember. Now the first question is this a redox reaction? Well, lithium as a metal, the neutral atom has an oxidation number of 0. Lithium here will be an ion for the reasons which I just talked about. It's going to have an oxidation number of +1. So lithium's oxidation number is changing. Chlorine's is also changing. So this is a redox reaction. So what we have to do is make sure that we balance lithium atoms and chlorine atoms, but also make sure that the number of electrons passed from the oxidation reaction is the same as picked up from the reduction reaction. Okay, so let's go ahead and do the first step, which is write out the half reaction. So we have lithium here is going to, again, we have lithium in an ionic compound. And so if that's the case, you have to remember what the charge of lithium is because it's a group 1 metal. It's going to be lithium plus, all right? And then we have chlorine. So we have chlorine here. And then this is going to chlorine. But here, chlorine in this ionic compound is a chloride ion, so it's going to be negative. Okay. Now, the next thing what we want to do is we want to balance atoms for these half reactions. And so we have 1 lithium atom here with 1 lithium ion, so there's 1 of lithium each. Here we have 2 chlorines on the left side, only 1 on the right side. So to balance the chlorides, we have to put a 2 here. All right? So what is the next step? The next step is to identify the oxidation reduction reactions. And so what may be helpful, again, is just thinking about this in terms of oxidation numbers. And so lithium is going here from an oxidation number of 0 to +1. So this looks like this is the oxidation reaction. And then we have chlorine going from an oxidation number of 0 to -1. See, it's a chloride ion. Each chloride ion has an oxidation number of -1. So this is a reduction reaction. Okay, so we figured that out. So now we have to figure out, as these reactions are written, how many electrons appear to be leaving the oxidation reaction and going to the reduction reaction. So again, I tend to sort of look at the reactions themselves and not their oxidation numbers. So here we have neutral lithium atom going to a positive lithium ion. It looks like it's losing electrons, so I'm going to write an electron like that. And then here with the reduction reaction, this is a little bit trickier to see. So this half reaction, you can see there's 1 molecule of chlorine, but there are 2 chlorine atoms here that need to pick up 2 electrons to become 2 chloride ions. So I'm going to write 2 electrons like that, okay? Now what we need to do is we need to balance the number of electrons being passed between the oxidation reaction and the reduction reaction. So you can see that there's 1 electron that's being lost in the oxidation reaction, 2 electrons being gained in the reduction reaction. So it looks like we're going to have to multiply the entire oxidation reaction by a coefficient of 2. Okay, so now what I'm going to do is rewrite these equations. And so we have 2 lithium goes to 2 lithium ion plus 2 electrons. And then what we have is 2 electrons plus the chlorine molecule goes to 2 chloride ions. Okay, and so now you can see that the 2 electrons here on the product side cancels out 2 electrons on the reactant side. So now we can write a final equation. So it looks like we have on the reactant side 2 lithium, right? And then we have a chlorine molecule, Cl2. And then it looks like we have 2 lithium ions and then 2 chloride ions. So this is not quite correct. And the reason is this. When you have lithium ions and chloride ions, that may imply that we're in an aqueous solution. But you might remember with lithium chloride, the state symbol was a solid compound. So we have to imagine these ions in a solid compound. So rather than writing 2 lithium plus 2 chloride minus, what we do is we write instead 2 and just imagine that the lithium ions are bound to the chloride ions like that. And so you might remember with ionic compounds, we write the elements not as ions, but in the compound we just write the elements with no charges. Okay, this appears to be balanced. So thank you for listening. We'll see you next time.